Hello, and thanks for joining me. My name is Nathan Chong, and I'm a Principal Applied Scientist at AWS. It's a privilege to speak to you because I know this audience has a great wealth of experience across the entire range of the embedded space. But one topic that unites us, that cuts across all our disciplines, is security. Because security is a collective, industry-wide responsibility which requires constant investment. This talk is about defense, how we might build more secure, more trustworthy systems using formal verification. It might surprise you to learn that formal verification, which we also call automated reasoning, is an active area of investment for AWS. Fundamentally, that's because these are techniques grounded in mathematical logic and proof, with the potential to unlock even higher levels of assurance of security and correctness. Levels of assurance that we could not obtain through other means. And this is a particularly compelling argument when it comes to foundational systems and components, which may form the bedrock for all manner of systems or applications above. Now, if this term formal verification is unfamiliar to you, then you're in exactly the right talk, because my aim is to clarify what it is, how it works, and how you can benefit from it, even if you're not the proofwriter yourself. And I'm going to do this using the concrete example of FreeRTOS, a real-time kernel and set of libraries for designing and building embedded applications. For example, if you were designing an IoT application, FreeRTOS might be one of the building blocks that you'd consider using. Here's a block diagram of an embedded application. The hardware is at the bottom and the application-specific logic is at the top. FreeRTOS is the common set of functionality in the middle. It's both the portable abstraction layer of the kernel, which provides features like task scheduling, memory allocation, and interprocess communication, and a set of common important libraries for features like network connectivity, over-the-air updates, and secure communication to cloud services. At AWS, we have a term undifferentiated heavy lifting to refer to building blocks like FreeRTOS. Undifferentiated because these building blocks are useful in all manner of different applications. And heavy lifting because it's hard work to build and secure core infrastructure. It's a full-time discipline in itself. So, AWS invests in undifferentiated heavy lifting so that you don't have to, which leaves you with more time to focus on your application-specific or product needs. It's this role as a foundational building block which makes FreeRTOS such a great choice for formal verification. Because if we can raise the level of assurance of security and correctness for FreeRTOS, then we correspondingly raise that level for all of its many users. In other words, if you choose to build on top of FreeRTOS, then you benefit from all of the heavy lifting and investment that's gone into it, which increasingly includes formal verification. In this talk, I'll focus on the verification work we've applied to the kernel. But this is just one of many pieces of verification that we've applied across FreeRTOS. And I encourage you to ask in the Q&A to find out more about those. Let's start with a discussion of the headline results, what we can accomplish with formal verification. The target of this work is the interprocess communication, or IPC mechanism, of the kernel. IPC is the abstraction that enables tasks and interrupt service routines to exchange messages. For example, an interrupt service routine might send sensor data through IPC to a task for further processing. And we want to verify the implementation of this feature. Not a model, not a simplified version, the code that you'd find in GitHub that you would compile against and that you would link against. Secondly, what are the properties that we now have even higher levels of assurance for? We've proven three important properties: memory safety, thread safety, and functional correctness. Let's go through each of these in turn. Memory safety is a foundational security property because ensuring the absence of memory issues such as buffer overflows or null pointer dereferences closes the door on all sorts of common security issues. Similarly for thread safety, which informally means absence of synchronization errors. And these can also be the sorts of issue that lead to security problems. Finally, functional correctness. This establishes that the implementation behaves exactly as we expect it to with no additional behaviors. So this is a fundamental correctness property. Taken together, holistically, these three properties are a strong signal of the security and correctness of the kernel IPC mechanism of FreeRTOS. Let's now turn to the question of why we could not have achieved these results through other means, in particular through testing. To do that, we'll have to examine the kernel IPC mechanism in a bit more detail. Internally, the key data structure for IPC is a queue. Queues enable tasks or interrupt service routines, ISRs, to send and receive messages of fixed size through a specific kernel API. As you might imagine, the queue is usually operating in a FIFO first in, first out manner. So in this queue, for example, the next task or ISR to send to the queue will have its message placed behind the orange message, and the next task or ISR to receive from this queue will get the blue one. Now, an interesting characteristic of this queue is that it has to work securely and correctly in a concurrent setting, meaning that we can have multiple tasks and multiple ISRs arbitrarily calling send and receive, and that these operations can overlap in time because of preemptive scheduling. Another way of saying it is to say that multiple tasks and multiple ISRs compete to use the same queue. And this is a very interesting property or characteristic when it comes to security and correctness, because we would like to know that the implementation is good regardless of the concurrent setting, which means regardless of the number of tasks or the number of ISRs or how they overlap. Let's take a closer look at why this is a problem. Here's a simplified scenario. I have 3 tasks here. What's the concurrent behavior of these tasks? It depends on the schedule of the system, which is to say the order in which these tasks execute in the presence of context switching. Context switches occur because of the task scheduler and are due to task prioritization and readiness. For example, in this schedule, we start executing with task 1 before switching to 2 and then to 3, and so on and so forth, until all of the statements of all of the tasks have been executed. Let's imagine that we had 10 statements in each task, and that a context switch could occur between any such statement. How many schedules does that give us? It's a rather large number. It's about 5 trillion. And the root cause is combinatorial explosion, which is to say the number of schedules grows exponentially as we increase either the number of tasks or the number of statements per task. And this is the root cause of all of the problems about reasoning for concurrent systems such as the queue of the kernel API, of the kernel IPC mechanism. I'd like to turn the tables to you for just a beat and ask you, given this concurrent setting and the problem that I've just described of combinatorial explosion, what tests or what methods would you think of using to assure yourself that the queue implementation is memory safe, thread safe, and functionally correct? I'll pause for just a beat to let you think. Well, combinatorial explosion is a real problem for testing. Firstly, there's the problem of being able to reliably trigger a specific schedule. This is non-trivial. It would require us to take control of the task scheduler and also have the ability to trigger events at cycle level accuracy. Secondly, there's the sheer number of schedules. Even if we could reliably trigger a particular schedule, it would still take us a long time to cover all of them when they number in the trillions. Lastly, and perhaps ultimately, we can't predict how any particular application will choose to structure itself between tasks and ISRs. We can't cover all of the manifest ways that the kernel API might be used. At best, we might be able to obtain some sort of exhaustive or bounded guarantee. For example, we might be able to exhaustively test 3 tasks, each of which can call up to 3 kernel API functions. But what if we wanted to go further? If we wanted to say that the kernel IPC mechanism was secure and correct in an unbounded case, meaning an unbounded number of tasks, an unlimited number of ISRs. Testing can't help us here. Now, let me interject and say that my point is not to rail on testing. Testing is extremely effective and important. Rather, my point is that we need a different, complementary approach if we're going to be able to tackle this problem of combinatorial explosion in the presence of unbounded assurances, or wanting to obtain unbounded assurances. And this is exactly the role of formal verification. So, how does formal verification deal with the problem of combinatorial explosion? The key idea is that we need a way to precisely capture what an implementation can do, but without running it. This might seem tricky, but you've encountered this idea before. It's a specification or a contract. That's another way of looking at it. And you'll commonly find specifications in documentation and interleaved into the source code as comments. For example, you might have a document for a comment saying this function, a document for a function which says this function expects that the first argument is a buffer of at least the length of the second argument. Now, the problem with these types of specification is that they're too informal. They're ambiguous because they're written in natural language. For example, what if that second argument to this function is a negative number? And crucially, there's no link between these specifications, these sorts of informal specification, and the implementation, except through testing and careful code review, which we've already established is insufficient to our aims of establishing unbounded assurances. So, formal verification requires us to take one further step, which is to formalize our specifications in logic, which is to say, to precisely capture the intent of the implementation in unambiguous mathematics. This is not always straightforward, and I'll come to the cost shortly. But what this opens the door and enables us to do is to link these formal specifications through mathematical proof to the implementation. And in this context, proof means machine checkable arguments or deductions, which we can get a program to check for us. It's this link between formal specification and implementation through proof, which is the essence of all formal verification techniques. So if you only remember one slide, this is the one that I'd recommend. So this is the core idea of how we're able to deal with combinatorial explosion through a specification that doesn't need to be run, but instead is mathematically checked against the implementation. And that's the theory. So what about in practice? Well, we need a tool that realizes or embodies these ideas. A tool called a deductive verifier. Verifast is such a tool from my co-author Bart Jacobs and his colleagues at KU Leuven. And it gives us two things: a rich, expressive logic for being able to express specifications, particularly about complicated components such as the kernel IPC, and a set of deductive principles for reasoning and ultimately being able to link these specifications to implementations in either C or Java code. If you're interested in the internals of FreeRTOS, then I highly recommend this paper. But my point here is actually to say that a key ingredient of this work is having tools that can scale to reasoning about real-world code such as what we'd find in FreeRTOS. And this is increasingly the case thanks to great strides in the academic community, the academic formal verification community. So now that we have clarity on what formal verification is and how it works, let's return to the results so that we can have a more nuanced discussion about the costs and benefits. We've already discussed the high-level results, proofs of memory safety, thread safety, and functional correctness in an unbounded setting, regardless of the number of tasks or ISRs. But an additional result that we obtained during the course of this verification work was that we uncovered 4 previously unknown findings. I go into more detail about each of them in the paper. But the point here is that these findings, each of them, had been undiscovered over a 15-year period of FreeRTOS being actively used. So it's testament to the thoroughness of formal verification techniques that we were able to find these issues and also prove that the fixes that we wanted to employ really did deal with them appropriately. So those are the results. What are the costs? These are not straightforward techniques to apply. They have some cost attached to them. The implementation of the kernel IPC in FreeRTOS is 700 lines of code. And it took us 3 person-months to verify them. That's the first cost, engineering time. But the second is the number of proof annotations that we needed to add to the code. As we'll see shortly, a proof in FreeRTOS consists of the implementation code with proof annotations added. The proof annotations are needed by the verifier to help it with its deductions as it tries to link together the specification and the implementation. And we needed 1,000 lines of, or about 1,000 lines of proof annotation, meaning we wrote more proof annotation than we had implementation lines of code. Now, this ratio is not unusual when it comes to this setting of trying to prove unbounded guarantees or assurances about concurrent code. Nonetheless, this cost of firstly writing and developing these annotations and secondly maintaining them is a cost that needs to be borne in mind when we're thinking about the costs and benefits of these sorts of technique. I think it's time that we went and took a look at what some proofs look like in the real. Let's go jump across to a terminal together. So here we are in the terminal. We've dropped into the root directory of a clean checkout of the FreeRTOS repository. FreeRTOS is on GitHub under an MIT license, and the same is true for all of the Q proofs. Let's jump across to where the proofs live. They live in this directory, and moreover inside this Q directory, where we've split the implementation of the kernel IPC across several different files, one file per function of the implementation. Firstly, let me show you a proof regression, meaning that we'll check that the kernel IPC implementation satisfies its formal specification of memory safety, thread safety, and functional correctness. And we can see that it takes a few seconds, which is to say the VeriFast tool lives up to its name. The point here is that once we have proofs, it's very easy to check them. And moreover, you don't need to trust me. You could reproduce these results locally by cloning the repository and verifying the proofs yourself. And I'd encourage you to do that. Next, let's look at a proof in more detail. But before I jump across, a brief warning. There's going to be a lot on the screen, and I won't be explaining everything. So don't worry if you don't understand all of the intricacies or all of the syntax. I want to give you an idea for what the essence of a proof looks like. And we'll start granular and then get into a few details. But if you want more information, then my paper has a detailed walkthrough. This is the FreeRTOS proof IDE. The first point to note is the green bar up at the top. This shows that the proof was successful. Let me make a trivial change to a comment so you can see the proof status go stale. The bar's gone grey. And now let's re-establish the proof by rerunning the analysis. Next, I want to point out how the idea of a formal specification is realized concretely. This statement here that starts with a requires is called a precondition. And this statement here that starts with an ensures is called a postcondition. Together, the precondition and postcondition are the specification of the function. They're the contract that FreeRTOS is checking that the implementation upholds. To be more precise, FreeRTOS ensures that whenever this function is invoked in an environment where the precondition is true, then if the function terminates, we know that the postcondition must be true. Next, let's look at how the proof is structured. Try not to read the code too hard, but look at the form. The proof is the code of the implementation. For example, this if statement or this call to a memcopy. But notice there are also these special comments which start with an @ symbol. For example, here and here. Each one of these is a proof annotation. So when I referred earlier to 1000 lines of proof annotation, this is what I mean. The proof annotations are not part of the implementation. That's why they're in comments. But they are part of the proof. They're required to guide FreeRTOS in its reasoning to establish that link between the formal specification and this implementation. Let me show you this concretely. If I comment out this annotation, then the proof no longer verifies. Writing these specifications and proof annotations are two of the primary costs of using this style of formal verification. But the beauty is that when we have a proof, we've established some very strong properties. So I hope you enjoyed that quick dive into the proofs, and that gave you an impression for what it might be like to use them and write them yourselves. This, however, is the central image that I hope you'll take away. This link between formal specification and proof. Formal specifications which allow us to capture precisely what an implementation can do, and being able to link them through mathematical argument or proof to the actual implementation without having to run the implementation. These are the core ideas and the essence of formal verification, and really the key to how we're able to unlock those even higher levels of assurance of security and correctness. Let me wrap up by saying that these principles that I've told you about with formal verification apply equally to many different types of system beyond FreeRTOS. And this is something that we're actively pursuing at AWS. So from this talk, I hope it gives you an appreciation for what that might involve, and also how you might benefit from these verification efforts, even if you're not the person doing the proofs yourself. I'll leave you with some resources and links to follow up on. And with that, I thank you for your time and look forward to all of your questions.